Let's talk about that little device you're probably holding in your hand right now. You know, this sleek rectangle of glass and metal. It's a modern miracle, for sure. But the real secret to its power isn't just the chip itself. Nope, it's the incredibly complex life support system that's wrapped around it. Today, we're going to pull back the curtain on the hidden world of semiconductor packaging.
I mean, seriously, just let that sink in. The phone you use to watch cat videos has more raw computing power than the machines that guided humans to the moon. It's an absolutely astonishing feat of engineering.
So, how in the world did we get here? How did we manage to shrink what was once a room-sized computer into something that slides right into our pockets? It's not just about making the silicon chips smaller. There's another piece of the puzzle, a really crucial part of the story. Okay, let's get into it.
The answer? The real magic lies in a technology that's often overlooked, but it is absolutely essential to making our modern world tick. We're talking about semiconductor packaging.
So what is it exactly? Well, at its core, you can think of packaging as a life support system for the chip. It's kind of like a suit of armor and a communications hub all rolled into one. It has to protect the incredibly delicate silicon inside, while also building all the electrical bridges for it to talk to the rest of the device. Yeah, and it's got to do a lot. It's this incredible 4-in-1 job. It's got to supply the power, it's got to connect all the signals to the main board, it has to get rid of all the heat the chip generates, and it has to protect it from stuff like moisture and dust. You see, without the package, the most powerful chip in the world is just a tiny, useless piece of sand.
You know, the story of packaging is really the story of a relentless race, a sprint that's been going on for decades, all driven by our endless hunger for smaller, faster, and more powerful electronics.
Just look at the journey we've been on. We went from big radios and TVs to personal computers. Then we somehow crammed all of that into a mobile phone, which then became a smartphone. And now we're powering cutting-edge AI and self-driving cars. Every single step demanded that we cram more and more transistors into a smaller and smaller space, all while using less power. It's a crazy challenge.
And this whole race was famously described by Intel's co-founder Gordon Moore. It became known as Moore's Law. And it wasn't just an observation. It basically became a self-fulfilling prophecy for the entire industry. It set the target, double the number of transistors on a chip every 2 years. And you can bet the packaging engineers were right there on the front lines figuring out how to make it all fit. To really get your head around that number, just think about computer memory for a second. We went from 64 kilobit chips to 1 gigabit chips. That's a 15,000 times increase in capacity. That is the kind of mind-boggling progress that the packaging had to keep up with. So how on earth did they do it? Well, the first big breakthroughs were all about how you physically connect the chip to the circuit board. And it's a pretty cool journey that takes us from, well, clumsy old legs to these revolutionary little balls of solder. Yep, you heard that right. The earliest solution was simple and made a lot of sense. Just give the chip some legs. These little metal leads would stick out from the package and you'd solder them right onto the circuit board. Simple enough. The first version was called the dual inline package, or DIP, and it had legs on 2 sides. But pretty soon that wasn't enough, so they invented the quad flat package, or QFP. And just like the name says, it put legs on all 4 sides, which, you guessed it, massively increased the number of connections you could make. But this whole legs approach had a big problem. You could only make them so small and put them so close together before they became way too fragile. Engineers were literally running out of real estate on the perimeter of the chip. So, what do you do? And this is where the big breakthrough happened. Someone had a brilliant idea. Why are we only using the edges? Why not use the entire bottom of the chip? And that's how the ball grid array, or BGA, was born. It replaced the legs with a whole grid of tiny solder balls. This was a complete game changer that opened up a whole new world for designing chips. So, with the bottom of the chip now fully covered in connections, the engineers looked up. The next frontier in packaging wasn't out, it was up. They were about to start building skyscrapers on a microscopic scale. The challenge was the same as always. How do you get more power in the same amount of space, or maybe even less? And the solution was just brilliant in its simplicity. If you can't build out anymore, you build up. You start stacking the chips.
Now, the process for doing this is it's mind-boggling. First, they take a silicon wafer and grind it down until it's as thin as a human hair. We're talking 30 micrometers. Then they stack these paper-thin chips right on top of each other and connect them all with these microscopic wires to create one single super powerful chip.
And this amazing 3D stacking tech led to something called the chip scale package, or CSP. And just like the name says, the package is almost the exact same size as the chip itself. This makes it absolutely perfect for cramming into small devices like our smartphones. It's different from the bigger BGA packages you're more likely to find in a laptop or a desktop computer.
But of course, the innovation didn't stop there. The next big idea was, hey, what if we could integrate the packaging right into the chip-making process itself? Make the whole thing more streamlined and efficient.
And this brings us to the newest frontier, wafer-level packaging. So instead of the old way where you'd cut all the individual chips out of the wafer and then package them one by one, WLP lets you package all the chips at once, while they're still part of the whole silicon wafer. It's just a massive leap forward in efficiency.
And the benefits are huge. The final product is thinner, which we all want. The electrical signals have shorter paths to travel, which means better performance. And hey, it even gets rid of the need for those expensive little gold wires, which helps lower the overall cost. It's really the holy trinity for manufacturing: thinner, faster, and cheaper.
And you can see the results for yourself. The move from a 28-nanometer process to a 17-nanometer one, thanks in a big way to these advanced packaging techniques, give us a nearly 40% boost in performance and a massive 49% improvement in power efficiency. This is exactly why your new phone feels so much faster and the battery lasts longer than your old one.
So, from clunky legs to microscopic skyscrapers, the evolution of semiconductor packaging has been nothing short of amazing. It's the silent, unsung hero of our digital age, always pushing the limits of what we think is possible. And as we look ahead, you have to wonder, if today's packaging gave us the smartphone, what incredible technologies will the next generation unlock that we can only dream of today?